Excellent. Thank you so much. So, thank you for inviting me, Adam. And today I will talk about developing data-driven robotic solutions for assembly tasks. But because the workshop is very much dataset-oriented, I want to focus on how we can employ a scalable human-to-robot skill transfer method in order to accomplish this goal. And I will give you some work that we have done in this field and the whole process of how we came up with this idea. So, the group, the name of my group is New Dexterity. This comes from New Robot Dexterity. We do a lot of hardware. We do a lot of robot grippers, hands, robot arm hand systems, humanoids, but we also work on teleoperation, telemanipulation, robot grasping, robot manipulation, benchmarking, and of course, autonomous operations in everyday life tasks, industrial tasks, manufacturing tasks. This is just the background of what we do in my group. Now, you know about the problem. The problem is that we have an increasing number of robots in industrial, service, and home environments. In industrial environments, we want, if possible, the robots to be used for flexible assembly, for flexible manufacturing. And we need to equip these robots with robust grasping and dexterous manipulation capabilities. Tasks that are very intuitive for us, for humans, they are difficult for robots and time-consuming to reliably implement on them or to learn them. And what we need a human-to-robot skill transfer. So how we take human experts and how we transfer their skills to a robotic system in a very intuitive and scalable manner. There are multiple ways of doing this. You can use manual robot teaching, you can use motion mapping, you can use programming by demonstration, you can use high-level supervision with reinforcement learning and many other things. And you may have less or more operator involvement or system autonomy, depending on the solution that you plan to use. We started this journey of simplifying human-to-robot skill transfer by doing programming by demonstration. And we started with what we call kinesthetic teaching and teleoperation-based teaching, two different techniques. So the idea is that we had a human demonstration. Then we were executing the task with the human expert. We were collecting some trajectories for the robotic system. And then, because the human demonstrations were suboptimal, we were optimizing the trajectories that we had collected in order for the robot to execute optimal trajectories in terms of path length or time. And let me show you some examples here. This is a collaboration with Mitsubishi Electric in Japan. We teach with kinesthetic teaching and with teleoperation-based teaching a robotic system on how to load a sample inside a processing machine. It's a peg and hold task mainly. And you can see the blue trajectories. The blue trajectories are the human demonstrated trajectories. And then from these trajectories, we derive with global planning and local replanning, the red trajectories that are optimal in terms of path length and time. But this was not fast. We wanted to be faster. We wanted to come up with some ideas that can allow us to scale up data collection, because essentially, in order to achieve the goal that we discussed about at the first slide, we need a lot of data. So I will show you how this approach looked like. You see here kinesthetic teaching, how it looks like. You put the sample within the hole, you record the blue trajectory, then you get this blue trajectory, you optimize it, and from the blue suboptimal trajectory, you get the red trajectory. But the whole teaching process takes a lot of time. And even if you optimize the trajectory, it is just 20% shorter. Teleoperation-based demonstration, same problems. You may have the human expert at a distance, and you can teleoperate a robot from a distance to do the same task. You still get a blue trajectory that is suboptimal, and you can optimize it, but it's not fast enough. So after that, we said, you know what, in industrial environments, it makes a lot of sense for people to have the CAD files. So we tried to do CAD-based localization of the components and integrate this with all the other approaches and methods that we were using in order to speed up the process. So we were getting, for example, here you can see the NIST board. We were getting the CAD files of the NIST board, and we had localization of the components with respect to the CAD, the position of the component in the CAD system. We developed also a graphical user interface that allowed us to select what tasks to be executed, the order, the sequence, and everything in order to speed up programming of a new task, of a new industrial task, by a user that is not an expert in robotic manipulation. And it looked like that. We exploit CAD interface together with the graphical user interface in order to identify certain primitive tasks. And then we use the assembly master that guarantees the execution of the task using also some compliance control. Very standard things. The good thing here is that we use CAD in order to speed up the process. And with this approach, we participated in the robotic grasping and manipulation competition of 2019, where we got the first place in Macau. This competition took place in Macau during IROS 2019. And you can see here the system using CAD-based localization and all the other methods in order to execute a series of assembly and disassembly tasks. But again, this was not perfect, as you can see here in the competition results, and this was also slow, and teaching new tasks takes time. So if the RGMC team decides to change completely the board, we need a lot of time in order to teach the tasks, the robot on how to execute the new tasks that have been integrated in the NIST board, in the new NIST board. So we decided to create this. What is this? This is a wearable human-machine interface that allows the human to become a proxy of the robot. So the human wears the end effectors and demonstrates how the task should be executed with the actual robotic end effectors. So we put the human in the loop, we remove the robot arm from the loop, and we let the human expert to decide how to do the task with the end effector. And this approach is hardware agnostic because the interfaces that we developed, this interface and the other interface, they are compatible with any kind of robot gripper or robot hand that you can find in the market today. We started executing a lot of tasks like grasping and manipulation of everyday life objects. The control interfaces allowed us to do also dexterous in-hand manipulation. So we were able to execute a plethora of complex tasks, even assembly tasks. And then we tested this system and we started comparing how the human-machine interfaces-based skill transfer is different from all the other approaches. The first thing is safety. We don't use any robot arms, so we can scale up very quickly data collection. And because we have the human in the loop, it is very safe for humans to collect data, even in environments where we have humans working in a factory or inside the house. We have by default the incorporation of human strategies because we exploit human intelligence and we derive human-oriented strategies for the execution of complex tasks. It is hardware agnostic, so you can use it with robotic grippers, without grippers, with any kind of gripper that you can find in the market. You collect real-world data that have slipping, rolling, friction, and all the other things that are hard to simulate. It is cost-effective because you don't need the robot arms, you need only the interfaces, so you can scale up very, very quickly. If someone wants to do large data collection, you can have 10,000 units developed in a matter of a couple of months. And because of the availability of the hardware and how easy it is to do experiments with this approach, we consider this as a very scalable and very fast solution when we compare it with all the other methods. And here, I will show you how it works. Here we use two parallel jaw grippers that we have designed in my group, and we execute a bimanual assembly task. So we need to disassemble the USB cable, and we need to pick the cable up with the other gripper in order to route it, and then insert it to the second connector that you see close to the human operator. So this is a very difficult bimanual manipulation task that is very hard to demonstrate with all the other approaches. For example, with kinesthetic teaching, imagine how many people you need in order to move the robot arms around. And here, we transfer the skill that we have demonstrated directly to the robot to be executed by the robot in a very efficient and very easy manner. We can do this when the environment is structured, for example, an industrial environment. We don't need multiple trials. We can just do one demonstration and transfer of the one demonstration to the robot. When the environment has some diversity, different object shapes, different poses of the board, different lighting conditions, then we need to collect a lot of data and have a repository of trajectories that we can trigger on demand for the execution of the task. And you see here how, again, it looks like the kinesthetic teaching. So the human trajectory is recorded and then mapped to the robot system with some local trajectory optimization in order to minimize the path length. But the good thing here is that, as you will see now, we transfer the strategy that has been employed by the human, and you see that the robot tries to mimic what the human did. It goes to insert the connector with an angle, because this is the best strategy possible for humans. And because humans used the same end effector, the same friction is there, the same slipping is there, the same rolling is there. So the robot is able to do it. And let me show you another example. Here we have another NIST board, and we have a flexible body. What is the flexible body? Is a belt. You cannot simulate a belt, so your only choice for collecting big data of belt assemblies is to collect data with an approach like this, with a wearable system. So we demonstrate how to pick up the belt, and we demonstrate how you need to push the belt in order to get fastened around the pulleys. And once we have demonstrated the task, the robot takes over and starts executing the task. You see that it is very slow for safety reasons, because the university doesn't allow us to do experiments with collaborative robots moving very fast next to humans or inside the lab. You can easily speed this up to the maximum speed available by the UR5 that we use for this humanoid. And how reliable this is? It works every time. It works every time with this kind of accuracy. If you need more accurate tasks to be executed, then it probably needs more data collection and larger datasets. And what we do, we also collect, as you see here, we superimpose the task execution instructions on an augmented reality system, and we collect also the commands of the human that the human operator identifies problems. And why we need to identify problems? Because we want to be able, when we compare the journey of the data collection with the HMI-based skill transfer approach with all the other approaches, we want to be able to give feedback on the hardware development. So we want to be able to understand why the robot grippers fail in order to give to the designers as soon as possible feedback on how they can improve the robot hardware. So For all the other approaches, and especially for humanoids, this slide is tailored for humanoids. You need to have some kind of hardware in order to start doing data collection. Or you can start even in simulation, but you will never do real experiments without having a prototype. We don't care about the whole hardware because we have the human in the loop. So we can start collecting data fast because we use only the grippers. And then we can start giving feedback from the failures of this approach to the designers while they are developing the next prototypes. And you speed up the whole process and you can collect data much, much faster because you don't rely on robots. So you don't need to call universal robots in order to ask for 10,000 units. You can easily design and you can easily develop and fabricate 10,000 interfaces in a matter of a couple of months. And the design feedback becomes new grippers, and the new grippers make the task execution much easier. For example, here, this is a new gripper that we have designed for parallel jaw gripper for peg and hold tasks based on the data collection that we have achieved with the new approach. We have some reorientation jigs, some regrasping operations, and we have also designed a rotary module for the screws because the gripper with the last degree of freedom of the UR5 is not fast enough in order to perform the fastening of the screws as quickly as possible. So we take all the design feedback into account and we generate new grippers that can make the robots perform even better. And some examples of how the new grippers work: very fast disassembly of screws with a rotary module that is like a drill, really. And the reorientation, the gripper that allows for reorientation, that can execute the tasks like the other videos that we watched today. But most of the times in assembly tasks, you may need to grasp a peg that is flat on the table and reorient this peg in order to execute the assembly task. Let me go to this part of the video. You see here, we grasp the peg that is flat, we reorient it, and we bring it to the hole where it gets assembled. So all these design adjustments come from the human feedback, that is the human feedback collected during the execution of the task with the gripper that is worn by the human operator. Yeah, that's all. Thank you so much. And I'm happy to take any questions.
So maybe you went over this already, but what exactly is being presented to the human in the HoloLens display? And how does that HoloLens display increase the load? This is more of a human-robot interaction question, an interface question. How does that load change the human performance? Because I know the HoloLens specifically is a little bit heavy on the head, and it looks like a pretty intense system to be wearing. It's very impressive work, but I can just imagine it's like a little bit ergonomically challenging to work with.
Yeah. Look, you don't need to wear it for the whole day.
Yeah.
I mean, in 30 minutes or 40 minutes, you can collect data that you cannot collect with weeks of experiments with other approaches. Now, the augmented reality systems will become lighter and more portable as we proceed developing new solutions. How we demonstrate the instructions, we superimpose markers or annotated parts of the NIST board, and we have a sequence of tasks that is given to the operator. And why we do this? Because we want to employ for operators people that are not roboticists. So, for example, we have been trying with philosophy students to see, can they use the system? Is it intuitive enough? Can they execute all the assembly tasks with very simple instructions? And I don't think that we have a real cognitive load because you just get a superimposed annotation of the environment.
One more question. You mentioned, is it intuitive enough? How are you measuring intuitiveness?
Yeah, I'm not doing a human-robot interaction research in order to actually measure intuitiveness. What I do is I see how much the cognitive load delays the operation and the execution of the tasks, and it doesn't delay them at all. So in terms of execution and how fast it is extremely fast. Now, there are certain questionnaires that we have identified in order to assess this, but we have not done that yet.
Great, thank you so much.
And then just last question, Minas, you mentioned about that you can perform these tasks at faster speeds from the dual manipulation. Have you had a chance to attempt doing that physically with your systems?
You mean to do kinesthetic and comparison of this approach with kinesthetic?
Yes.
Or something like that? Yeah, we have done everything. And we have created also, let me show you here. We have compared all the teaching methods possible in robotics. HMI is the one that I showed you today, teleoperation-based, simulation, reinforcement learning, kinesthetic, or even pentant that is used very much by industry. And we have identified execution times, advantages, disadvantages, overheads, cost overheads, time overheads, everything. Yeah, happy to discuss this offline because it will take a lot of time.
No, but it's great to know that you've done that amount of analysis. Fantastic. All right, Minas, thank you very much.
Yeah, thank you for having me.